We're going to be looking at test 5. So the first question listed below are systolic blood pressure measurements obtained from the same women. So this is a paired sample. And so this is one woman here, and that's the reading for her right arm, and that's the reading for her left arm. And here is our second woman. So we have 1, 2, 3, 4, 5 women in this sample. So if I look at the answer sheet, there's a couple of things that we can do. This is a linear correlation problem. And so the null hypothesis is there's nothing fishy going on, nothing out of the ordinary. These two lists are unrelated. There's no correlation, no linear correlation. And of course, the alternative hypothesis is these readings are related somehow, that there is a linear correlation. All right, so let's get the correlation coefficient. Well, in order to do that, we have two rows of data here. The first row is going to be my x values for my points, the x coordinates, and the second row is going to be my y coordinates. So I'm going to put the first row in a list, and I'm going to do the same to the second row. So let me press the stat button. Let's clear out two lists, and I'll clear list 1, and list 2. And then I'll press the stat button again, go straight to the editor, and I'm going to put these readings. So in list 1, I'm going to have 102, 101, 94, 79, and 79. Then in list 2, I'm going to have 175, 169, 182, 146, and 144. Now, if I want to get the correlation coefficient R, let's see what happens if we just go to Calc and come down here to linear regression and tell it you want to do linear regression with list 1 and, list 2. I get an A and a B for an equation of a line, but I don't get the correlation coefficient. So why is that not showing up there? Because you have to turn your diagnostics on. So to do that, I need to get into the catalog. So I need to press second and then the 0. And I need to come down here to diagnostics, if I remember it right. And I want diagnostics on. So press enter. Done. Now let's try that again. Let's go to Calc. Let's go down to linear regression with list 1 and list 2. And I do have R. That is my linear correlation coefficient. And I want to take that to 3 decimals like it asked me to. And so that's going to be approximately 0.867. Now, what is the critical value? Well, for the critical value, I'm going to need to use table A6. So here's table A6. In the problem, we were told to use a 0.05 significance level. So alpha is 0.05, and N is the number of pairs of data that we had. 1, 2, 3, 4, 5. N is 5. So alpha is 0.05 and N is 5. And so the chi-squared critical value is 0.878. Now, what we have from this is that the absolute value of R, well, since it's a positive number, it's going to be the same, is actually less than the critical value. And so, since we have, the test is, if the absolute value of R is greater than the critical value, then we were to conclude that there was a linear correlation. But that is not the case here. So we cannot conclude a linear correlation. So I'm not going to want to reject this. All right, sorry. Let me get the calculator off. So the absolute value of R was equal to what it was, but that was smaller than 0.878, which was a critical value. So it's only if the absolute value of R is greater than the critical value that you can conclude that there is a linear correlation. That was not the case here. And so we certainly are not going to reject the null hypothesis. We're going with the null hypothesis. So we fail to reject the null hypothesis. And there is not sufficient evidence for a linear correlation because the absolute value of R was smaller than our critical value. So our regression line here is not applicable because we don't have a linear correlation. Now, predict the systolic pressure in the left arm. The left arm was the Y values. So we're supposed to predict Y if the systolic pressure in the right arm was an X value, if X is equal to 100. Well, there was no linear correlation, so there's no regression line. If there's no regression line, that means that the best predictor for Y is the mean value or the average Y. Now remember, Y was list 2. So I'm going to go back and go to calc, and just at 1var stats, I'm going to ask for list 2, and the average value, the mean for list 2 for my Y values is 163.2. That is the best predictor that we have because there was no linear correlation. Okay. Listed below are the number of commuters, number of parking spaces, and use a 0.01 significance to find the correlation coefficient. Again, this is another linear correlation problem. So the null hypothesis will be no linear correlation. The alternative hypothesis will be there is a linear correlation. To get the correlation coefficient, again, I'm going to have to put the first row, which is my X values, into a list, and the second row, which is my Y values, into a list. So to do that, I've got to clear out my old list 1 and list 2. And then I'm going to get into the editor, and in list 1, I'm going to have 3, 4, 5, 3, 1350, 1126, 3120, 2641, 277, 579, and 2532. Okay, and now list 2, I'll scroll over, and I'm going to have 1653, 676, 294, 950, 1216, 179, 466, and 1454. Okay, so to get the correlation coefficient, I'm going to do stat, go over to calc, come down here to linear regression, and tell it I want it to do linear regression with list 1, comma, and list 2, and press enter. My correlation coefficient is R, and taken to 3 decimal places, that's going to give me 0.901. So now my critical value I get from A6. So N is the number of pairs we had, and I had 1, 2, 3, 4, 5, 6, 7, 8 pairs of data there. So N is 8, and we had a 0.01 significance level. So N is 8 and alpha is 0.01, and those match up at 0.834. So my critical value is 0.834. That is not a chi-squared critical value. I can't remember if I said that on problem 1, but it's not so if we're just doing correlation coefficient. That's my critical value. All right, so what do we have here? The absolute value of R is, I'm going to get the same because it's positive. This time it's greater than 0.834, which is the critical value. So absolute value of R is greater than the critical value. And when that happens, we conclude that there is a linear correlation. And so we are going to reject the null hypothesis because the null hypothesis said that there was no linear correlation. There is sufficient evidence for a linear correlation. So now that we do have a linear correlation, we need the regression line. And so I can get that accurate to 3 decimal places. I get that from linear regression. It's already on my screen. So the equation is this y hat equals A, and I'm going to take A to 3 decimal places. So that's 0.409 times x plus B, which is that 89.488. Okay, so I do have a regression line. Predict the number of parking spaces if a station has 2,804 commuters. Okay. Predict the number of parking spaces. Parking spaces is Y. So predict Y if it has 2,804 commuters. Commuters is X if X is equal to 2,804. And so I'm going to plug in X into this equation. So the predicted value, so the predicted number of parking spaces is going to be equal to 0.409 times X plus 89.488. And so I'm going to do that on the calculator. 0.409 times 2,804 plus 89.488. And so the number of parking spaces, I want that to be a whole number. And even if that had been 1,236.9, I still would have said 1,236 because you can't have 1.5 parking spaces. Okay, so that's the number of parking spaces that we've predicted. Because there was a linear correlation, I use a regression line. I have a regression line because there is a linear correlation. On the problem before, there was no regression line because there was no linear correlation. Now, randomly selected non-fatal occupational injuries are categorized. So on a Monday, there happened to be 23. There happened to be 23 injuries or illnesses, people calling in sick. On a Tuesday, there was 23. Okay, so this is now, we're getting into chapter 11. And so we're looking at goodness of fit. So with goodness of fit, the null hypothesis is there's nothing fishy, that the days of the week and the number of people who call in sick or have injuries are not related. The days of the week, so whether or not you get injured is completely independent, or whether or not you call in sick is completely independent of the day it falls on. So injury and illness, and the main thing here is independent of the day. So the alternative hypothesis is that there is a relationship between injury and illness and the day that you call sick on. So there's some kind of dependency there. Now, what is the expected number of illnesses or injuries? Okay, well, how many categories are there? We have 1, 2, 3, 4, 5. So K is equal to 5. And what is the probability that if you were to get sick on a random day, that you get sick on a Wednesday, if everything is equal? Well, you have a 1 out of 5 chance of getting sick on any particular day. Okay, and so the expected number is equal to n times p. And what is n? N is all of the illnesses and injuries. So n is going to be equal to 23 plus 23 plus 21 plus 21 plus 19. So the exact answer would be 107 over 5. Okay, or 21.4. Either one of those is fine. So on any given day, we would expect 21.4 illnesses if there's nothing fishy going on. All right, if people aren't saying, oh, it's a Friday, I'll call in sick. All right, if nothing fishy's going on, we would expect that many every day. We don't get that many every day. The numbers are different, but is the difference statistically significant enough to say there is something fishy going on? What is the chi-squared test statistic? Well, the chi-squared test statistic is going to be this number. So my observed values are what we observe, what's reported every day. So that's going to go into list 1. So I'm going to need to clear out 2 lists here. Clear out list 1 and list 2. Okay, so in list 1, I've got 23, 23, 21, 21, and 19. Now, the chi-squared test statistic is going to be the summation of all of these. Okay, so I need list 2 where each thing in list 2 is one of these. So the first thing in list 2 would be 23, the O value, minus the expected value, which is 21.4, all squared divided by 21.4. But I don't want to do that for each one. So what I'm going to do is I'm going to come over here, I'm going to go up to list 2, and I want to define list 2 to be the O value, so each thing in list 1, so second one, minus the expected value, which I calculated to be 21.4, close parentheses, squared, divided by the expected value. And then as soon as I press enter, it will generate each one of those for list 2. So now I've got each of these separate ones, and my chi-squared test statistic will be all of them added up together. So I need to take list 2 and add everything up in it. So stat, and ask it to do that with list 2, and I need everything added up. So right here, the summation, because it's calling everything in list 2 an X value. Okay, some students choose this thinking that that's chi-squared. That is not. That's the summation of everything in the list squared, each individual thing squared. So this was shown in class. This, the summation of the x's are everything in list 2, is what I want. And we've been told to take that to 3 decimal places, so that will be 0.523. 0.523. Now, what is the chi-squared critical number? I get that from a chart. That will be that chart A4. So, what are the degrees of freedom going to be? Well, look down here at the bottom. Degrees of freedom, we're going to have K minus 1 for goodness of fit with K categories. And I have 1, 2, 3, 4, 5 categories. So degrees of freedom is going to be 4 for this. And what was the alpha for this one? Alpha is 0.01. So that's what I want to get from this chart. Alpha is 0.01. There it is. Degrees of freedom is 4. So 13.277. Now, label your answers to C and D in the given distribution. This is a chi-squared distribution. Now, the critical number, as we have learned now for weeks, the critical number is the number that separates the rejection zone from the zone where we accept. So this is always our critical number. Our critical number here is 13.277. That's my critical value. What was the test statistic? It is 0.523. Where is that on this line? 0.523 is much smaller than 13.277, so it's way over to the left here. So that's where my test statistic is. The test statistic in this is not in the rejection zone. So we do not reject the null hypothesis, i.e., fail to reject the null hypothesis. All right. If I fail to reject the null hypothesis, it means I'm accepting the null hypothesis. So the injury and illness is independent of the day. Oh, my dogs are howling. So nothing fishy going on. Goodness. All right, shush. I might put this on hold until I can quiet them down. Okay, we'll see how long that lasts. I just yelled out, shut up. We'll see how long it lasts. Okay, and finally, a retrospective study was done to investigate a relationship between the colors of helmets worn by motorcycle drivers and whether or not they are injured or killed. These are all of my observed values. So now we're going to have contingency tables. And so my observed values one, two, okay, so these are all my observed values, and I'm just going to copy them down here. 491, 377, 31, 170, 55, 213, 112, 8, 70, and 26. Okay, so contingency tables, the null hypothesis is always nothing fishy is going on, so there's no relationship between the color of the helmet and whether or not you get injured. So injury is independent of helmet color. Nothing fishy going on there. The alternative hypothesis is there is something fishy. There is a relationship. There is an influence. So whether or not you get injured, injury does depend on the helmet color. It does have an effect. Okay, enter the expected values. Okay, where does this guy live? He's in row 1, column 1. So this is E11. And E of 11 is going to be the row 1 total times the column 1 total divided by the grand total. So let me do these totals here in a different color. So what is our row 1 total here? That's going to be 491 plus 377 plus 31 plus 170 plus 55. So my column 1 total is 1, 1, 2, 4. So I'm doing that in red. Know how clear that is. That's my row 1 total. My row 2 total is going to be 213 plus 112 plus 8 plus 70 plus 26. So my row 2 total is 429. And so what's my grand total? 429 plus 1124, which is 1553. What's my column 1 total? My column 1 total is 377 plus 112. My column 2 total is 39. My column 3 total is 240. And my column 1, 2, 3, column 4, column 5 is 81, I think. 81. Okay. And so if I add these up, I should also get the same grand total. So 81 plus 240 plus 39 plus 489. Okay. Oh, sorry. I was missing that one out. Plus, and 491 plus 213. Okay. 704. All right, I got it right now. Column 1 total, column 2, column 3, column 4, column 5. And so this plus 704. All right, why don't they match? 491 plus 213 is 704. 377 plus 112 is 489. Okay. 31 and 8 is 39. 170 plus 70 is 240, and 55 plus 26 is 81. 81 plus 240 plus 39 plus 489 plus 704 is 1553. Okay, so somehow I missed it before, but it's okay now. So that's my grand total. Now, this lives in row 1, column 1, so that's E11, and it will be equal to the row 1 total, which is 1124, times the column 1 total, which is 704, divided by the grand total, 1553, and we want to round that to 2 decimal places. So 1124 times 704 divided by 1553. If I round that to 2 places, that's 509.53. So that's E11, which is 509.53. Okay. What's this guy? It's E12. I am not going to do all of them. I'll do the first 2 and then let you do the rest to check. Row 2, column 1. It will be the row 2 total times the column 1 total divided by the grand total. So this will equal the row 2 total, which is 429, times the column 1 total, which is 704, divided by 1553. 429 times 704 equals, divided by 1553. So to 2 decimal places, that's 194.47. So row 2 total times column 1 total, 429 times 704, all divided by the grand total, 1553, gives me 194.47. Okay, so notice it's row first, column second. So E21 is row 2, column 1, my expected value. So let me do another random one. How about row 1, column 4? What is the expected value in row 1, column 4? It would be the row 1 total times the column 4 total, all divided by the grand total. So that would be row 1 total, 1124, times column 4 total, which is 240, divided by 1553. And let's see what we get there. So 173.70. So that is my expected value in row 1, column 4. Row 1 and column 4. What about this guy here? Where does he live? He's in row 2, column 5. What's the expected value for row 2, column 5? That would be the row 2 total times the column 5 total, all divided by the grand total. So row 2 total is 429 times column 5 total, 81, divided by the grand total, 1553. So to 2 decimal places, 22.38. So I'm going to go ahead and write in the rest of them. I'll leave those for you to check. So what's the expected value for row 1, column 2? It's hard to write over that. Expected value for row 1, column 2. That's going to be 353.92. 353.92. 353.92. All right, that's crumbling. 353.92. For row 1, column 3, that's 28.23. Row 1, column 5, expected value is 58.62. Row 2, column 2, expected value 135.08. Row 2, column 3, expected value 10.77. Row 2, column 4, expected value 66.30. And that should get all of them. Now, I want to put these in a list. I want to put my observed values in a list and my expected values in a list. So observed values is going to be list 1, but first, and I'm going to need to make room for 3 lists. Clear list 1, clear list 2, and clear list 3. So what are we going to put in list 1? My expected values, row by row. So 491, 377, 31, 170, 55, 213, 112, 8, 70, and 26. Those are my expected values. Those are my observed values. List 1, observed values. List 2 is going to be my expected values. So 509.53, then 353.92, then 28.23, then 173.70, then 58.62, then 194.47, 135.08, 10.77, 66.30, and 22.38. Okay, list 1 are my observed values. List 2 are my expected values. Now, what is my test statistic going to be, the chi-squared test statistic? Well, it's going to be, find the formula. It's going to be the summation of each observed value minus its corresponding expected value squared over its corresponding expected value. So I need to make up a list 3 of all of these separate ones and then add them all up, and that will give me my test statistic. So I'm going to go over here to list 3, go up, and then I'm going to define it. Parentheses, my observed values, which are in list 1, minus its corresponding expected value, which is in list 2, close parentheses, square it, divided by its corresponding expected value, which is list 2, and press enter, and that will generate list 3. Now, the chi-squared test statistic will be the sum of everything in list 3. So I want to do statistics, calc, 1 var stats on list 3, and I want the summation of the individual things in list 3, and it's calling the individual things in list 3 X. So this is my test statistic, not the X squared. That is not a chi-squared. That's the summation of all the things in list 3 squared, each individual thing squared. This is what I want, the summation of everything in list 3. So taken to 3 decimal places, that's 9.967. 9.967. That is my test statistic. Now, what is the chi-squared critical value? Well, I get that from list A4. If you're doing contingency table, the degrees of freedom is going to be the number of rows minus 1 times the number of columns minus 1. So the degrees of freedom is going to be, I have 2 rows, and how many columns did we have? We had 5 columns, and 5 minus 1, R minus 1 times C minus 1. We had 2 rows and we had 5 columns. So that'll be 1 times 4, which is 4. So degrees of freedom are 4. And what was alpha for this problem? Use a 0.05 significance level. So degrees of freedom is 4. So I have 9.488 for my critical value. Label your answers. The critical value is always the one that separates the rejection zone from the zone that's acceptable. So my critical value is 9.488. That's my critical value. Now, what is my test statistic? It's 9.967. Where is 9.967 on this line? It's bigger than 9.488. So it's going to be to the right. That is my test statistic. What has happened? The test statistic is inside the rejection zone. And so we reject the null hypothesis. I reject the null hypothesis. Null hypothesis said there was no relation. And so it does appear that helmet color influences driver safety.